The B-17's ball turret, officially the Sperry A-2 ball turret, was one of the most distinct and dangerous fighting positions of World War II. Hanging beneath the belly of the flying fortress like a glass sphere full of guns, it offered unmatched visibility and downward firepower, but at the cost of extreme vulnerability. This compact, rotating weapons pod was designed for one purpose: protect the bomber from fighters attacking from below, a blind spot that enemy pilots frequently exploited. While similar turrets were installed on aircraft like the B-24 and B-32, some of which could retract for landing, the B-17's ball turret was fixed in place. Contrary to popular belief, it did not pull into the fuselage. Once airborne, it stayed fully exposed to the slipstream and every threat the bomber encountered. In this film, we focus on the A-2 variant, the version mounted on the B-17F. It was compact, heavily engineered, brutally cramped, and a critical line of defense for crews flying deep into enemy territory. My name is Marcus Reed, and this is Iron Blueprint. The Sperry A-2 ball turret was a compact, self-contained combat module just 44 inches in diameter and weighing roughly 850 pounds. From the outside, it looked like a smooth glass sphere suspended beneath the bomber. But nearly every surface hid specialized engineering. Two curved plexiglass domes were mounted on support brackets along the sides of the turret, giving it its distinctive globe-like profile. These domes didn't just shape the turret aerodynamically, they shielded the rotating drive mechanisms from freezing temperatures at altitude. At the very front sat a steel-reinforced center section built around the gunner's primary sighting window. This piece held 4 angled plexiglass panels, arranged to give the gunner the widest possible downward view, while keeping the structure strong enough to endure slipstream pressure and flak bursts. Opposite that front section was the entry assembly. Cast from aluminum for strength and weight savings, it formed the rear half of the turret and curved upward into the sphere. This entire piece doubled as the gunner's backrest once inside the turret, providing both structural support and limited ballistic protection. Although the A-2 turret appeared seamless from the outside, it was actually a carefully layered combination of steel armor, cast aluminum framing, and plexiglass windows, each chosen for a precise balance of resilience, weight, and visibility. All of it had to survive the elements, absorb vibration, maintain balance during rotation, and keep a gunner alive in one of the smallest fighting compartments ever flown into combat. For the A-2 ball turret to function, it needed a way to rotate freely beneath the aircraft while staying firmly anchored to the fuselage. The engineering behind that movement was far more complex than the turret's small size suggests. At the heart of the system was a 46.5-inch circular opening cut into the belly of the B-17. Into this opening sat a slightly larger trunnion ring, the fixed mounting point that carried the turret's entire weight. Bolted to that ring was the trunnion ring support assembly, a reinforced frame that rotated smoothly as the turret turned. This component acted like the turret's backbone, strong enough to hold the entire spherical structure, but engineered to pivot with almost no friction. Next came the harness system, a set of curved structural arms secured to the support ring. This harness performed 3 critical roles. Structural rigidity. It tied the rotating turret securely to the aircraft's frame. Smooth rotation. A swivel bracket at the top let the entire assembly spin freely under power. Electrical conduit. The harness served as the turret's power pathway. Because the turret could rotate endlessly in either direction, normal wiring would twist, snap, or tear apart almost immediately. To prevent that, all turret wiring ran into a sealed housing inside the harness, where rotating brush connectors passed electrical current without cables ever needing to twist. It was a brilliantly simple solution to an incredibly difficult engineering challenge: how to keep a fully armed, fully powered rotating module connected to a bomber moving at 150 plus mph in freezing air. The entire system was so effective that the gunner could spin the turret continuously without interruption, maintaining a stable firing platform even as the aircraft climbed, banked, or entered combat. Before a B-17 ever left the ground, there was one rule every crew member understood clearly: no gunner was allowed inside the ball turret during takeoff or landing. The reason was simple and deadly practical. The twin, 50 caliber guns on the A-2 turret extended 36 inches below the sphere, far lower than the aircraft's ground clearance. If a gunner were inside the turret when the aircraft accelerated down the runway, even a small dip or bump could drive the guns into the ground, likely destroying the turret, crippling the aircraft, and killing the gunner instantly. To prevent this, the guns had to be locked in a very specific position, elevated to the maximum 85 degrees upward bias, pulled nearly flush with the fuselage, mechanically locked before taxi, takeoff, or landing doors. Only when the bomber reached 9,000–10,000 feet high enough to avoid turbulence and low-level hazards would the ball turret come alive. At that point, the gunner prepared to enter, but only after the aircraft was stable and still far from enemy territory. The turret remained locked through the entire climb, unmanned and motionless, until the crew confirmed the sky was clear. Oxygen wasn't yet required, and the aircraft was safely underway. This strict procedure wasn't just aviation discipline, it was survival. The ball turret was one of the most vulnerable positions on any World War II bomber, suspended below the aircraft like a glass bubble. Keeping it empty until the bomber was well into the climb ensured both the gunner's life and the aircraft's integrity. Once the B-17 climbed between 9,000 and 10,000 feet, one of the most dangerous jobs in military aviation began. It was time for the ball turret gunner to enter his sphere. Inside the fuselage, the gunner started by unlocking the entire turret assembly, releasing the handbrake on the trunnion ring, disengaging the elevation clutch to free the elevation gearing, using the hand crank to rotate the turret so the guns pointed straight down. Only in this exact orientation did the entry hatch swing fully open inside the fuselage. With the elevation gear re-engaged from the inside, the turret was ready. Then came the part every gunner remembered for the rest of their lives. Dropping in, the gunner lowered himself feet first into the tiny opening. His boots slid into the two metal footrests on either side of the main sighting window. His knees folded tightly toward his chest, his back pressed against the turret's curved steel floor. His head rested on the closed hatch behind him. It was a fetal position, locked inside a steel and glass sphere just 44 inches across. Once settled, the gunner reached up and locked the hatch. From that moment forward, he was sealed inside a combat capsule suspended under the bomber's belly with no way out unless the aircraft descended below 10,000 feet or survived the entire mission. This was the reality of the B-17 ball turret. No space, no comfort, no margin for error, only the gunner, his weapons, and the enemy below. Once sealed inside the sphere, the gunner began transforming the turret from a silent steel capsule into a fully powered combat station. The first step was simple but crucial, bringing the turret to life. With almost no room to move, the gunner reached up and activated the switch box, energizing the electrical system that powered the turret's rotation and sighting equipment. Right above him sat the K4 gun sight. A flip of a switch illuminated its reticle, the only visual tool he had to aim through the main sighting window between his legs. Then came the life support systems. In temperatures that could drop to 50 degrees Fahrenheit, survival depended on the heated gear plugged into the turret's narrow interior. The heated flight suit connected into a receptacle beneath the gunner. The oxygen hose clicked into the regulator just below the hand control panel. The oxygen gauge had to read 400 pounds per square inches, and the small flow indicator needed to spin proof that breathable air was flowing correctly. Even communication was adapted to this cramped prison. With both hands occupied during combat, the gunner used a push-to-talk switch positioned near his right heel, operated by tapping it with his foot. Next came the armament systems. Two selector switches controlled the left and right 50 caliber machine guns. Because the firing buttons on the hand grips sat dangerously close to where thick gloves might brush them, the weapon selectors stayed off until actual combat. Charging the guns, the most awkward job in the air. Charging a 50 caliber Browning was normally trivial. Inside the ball turret, it was nearly impossible. The gunner's ears sat inches from the slide assemblies. There was no space to pull the charging handles in a straight line, so the engineers designed a workaround. A pulley system. Two cables ran from the gun slides, through multiple pulleys, and down to a pair of cross-armed handles near the gunner's feet. To charge the guns, the gunner leaned forward and pulled both handles toward his chest, using the mechanical leverage of the pulleys to rack the bolts. He had to do this twice for each gun. No armor, no parachute, only a harness. The gunner wore no flak vest. There was simply no room. He also didn't wear his parachute, that too was impossible inside the sphere. Instead, he wore only the harness, with the parachute stowed elsewhere in the fuselage. If he ever needed it, he would have to climb out first. Independent oxygen system. Because the turret rotated freely through 360 degrees, it couldn't connect to the B-17's main oxygen system. Hoses would twist and tear, so the A2 variant carried its own. A pressurized oxygen bottle mounted inside the fuselage, a hose that rotated with the turret. About 2 hours of oxygen. It was the responsibility of the waist gunner to replace the oxygen bottle every few hours or sooner if the ball turret gunner called up for help. The environment inside the sphere. The turret wasn't insulated, wasn't heated, and wasn't pressurized. Any exposed skin could freeze instantly to the metal interior. This is why gunners wore leather flying suits, electrically heated clothing, fur-lined boots, thick gloves or mittens. Inside this tiny bubble suspended beneath a bomber, isolated from the rest of the crew, the gunner became the aircraft's most vulnerable protector. Cold, alone, pressed into a steel sphere with 2 machine guns and a glass window aimed at the enemy. And with the turret fully powered, the real work began. Inside the A2 ball turret, movement didn't feel like flying. It felt like wearing a machine. Once the gunner powered up the system, the turret transformed from a steel capsule into a fully motorized, gyroscopic combat platform 1, capable of rotating 360 degrees horizontally and moving 90 degrees vertically in a matter of seconds. Every movement came from a single control unit mounted above the K4 gun sight, inches from the gunner's face. The hand control unit, the heart of the turret. The gunner didn't steer with pedals or sticks. He gripped 2 pistol-style hand controls, one in each hand. The control logic was inverted by design. Push the grips to the left, turret rotates right. Push the grips to the right, turret rotates left. Push forward, turret depresses downward. Pull back, turret elevates upward. It sounds counterintuitive until you imagine working upside down inside a sphere. The gunner wasn't seated upright. He was curled in a fetal position, with the world inverted beneath him. So the controls were engineered around his reality, not around traditional pilot orientation. Smooth motion under fire. What made the turret truly remarkable was how it responded. The harder the gunner pushed or pulled, the faster the turret moved. This proportional control allowed for fine corrections when lining up a target, rapid sweeps when hunting fighters attacking from below, combined rotation and elevation for smooth, curved firing arcs. With both motors working, the turret could rotate 360 degrees in 8 seconds, move from full depression to full elevation in just 3 seconds. That speed was essential. Enemy fighters didn't wait. Extreme maneuvering in zero space. Movement inside the turret wasn't graceful, it was survival. The gunner's knees were drawn to his chest. His feet rested beside the sighting window, his head pressed against the rear hatch. Every shift of motion came from forearm strength, not from whole-body leverage. Yet, even in that confined darkness, he could track aircraft streaking past at 300 miles per hour. He became part of the turret, one organism, one machine. Safeguards against disaster. To protect the aircraft, Sperry engineers added a mechanical safeguard called the forward-facing cam. As the turret rotated toward the B-17's propellers, a pin touched the cam and cut power to the gun-firing solenoids, prevented the gunner from shooting the aircraft's own engines. But the system wasn't perfect. The cam did not account for open bomb bay doors. During a bomb run, there was nothing to stop the gunner from firing directly into the aircraft's open belly. One more sign of how primitive World War II safety engineering truly was. Manual cranking, the last resort. If electrical power was lost, the turret didn't become useless. It became manual. 2 hand cranks allowed the gunner to move the turret slowly, painfully inch by inch. This method was too slow for combat, too exhausting for sustained use, but essential for escape. When returning home or when preparing to bail out, the turret had to be rotated so guns pointed straight down, aligned with the exit hatch, and positioned for safe evacuation. Without manual cranks, a power failure could trap the gunner permanently inside the turret. Before a ball turret gunner ever faced enemy fighters, he had to complete one of the most difficult and uncomfortable actions on the entire B-17, entering the turret in mid-air. Unlike the B-24, the B-17's ball turret couldn't retract. It hung fully exposed beneath the fuselage, a glass and steel sphere suspended in the slipstream. That meant the gunner could only enter once the aircraft was high enough, stable enough, and far enough from takeoff risks. The descent into the sphere, at around 9,000 to 10,000 feet, before oxygen was mandatory but after climb-out was complete, the ball turret gunner prepared to enter. The process began with unlocking the turret. Release the handbrake beside the turret ring hand crank. Disengage the elevation clutch. Freeing the vertical mechanism, hand crank the turret until the guns pointed straight down. Only in that exact orientation did the entry hatch inside the fuselage fully reveal itself. The gunner reached in through the open hatch and re-engaged the elevation gear using the internal clutch, locked the system so the turret wouldn't drift mid-entry. Then came the hardest step, climbing inside, sliding into combat position. With the aircraft vibrating and cold air seeping from below, the gunner lowered himself straight down through the hatch, feet first. His boots slid into the tiny footrests on either side of the sighting window. His knees folded toward his chest. His back curved against the armored steel plate, forming the bottom of the turret. His head rested against the interior side of the hatch door now closed behind him. Inside, there was no room to sit, kneel, or even stretch. The gunner curled into a fetal position, perfectly shaped to match the turret itself. Everything in this space was inches away. The guns, the ammunition cans, the turret motor, the sighting glass, the hand controls. Once locked inside, he was sealed away from the rest of the crew alone, in a cold, humming metal sphere, suspended beneath a bomber flying into enemy territory. Securing the position, before anything else, the gunner locked the hatch, powered up the turret from the switch box, activated the gun sight, connected his heated suit, connected his personal oxygen system. Only then was the turret live. Only then did the gunner truly become the aircraft's last line of defense from below. Once the gunner was sealed inside the turret, the real work began. The sphere wasn't just a firing position, it was a miniature combat cockpit with its own power, oxygen, weapons, and survival systems. And every step had to be done correctly, because once the B-17 entered enemy territory, mistakes meant death, bringing the turret to life. The first action was simple but critical. Lock the hatch. A loose hatch could open under G-forces, turbulence, or recoil, trapping the gunner halfway in or out, a deadly situation beneath a moving bomber. With the hatch secured, the gunner powered the turret, flipped the activation switch on the switch box, turned on the K4 gun sight, checked the power indicator. Cold air and engine vibration filled the sphere, but the turret now hummed with electrical life, suiting for survival. Because the gunner couldn't move his arms freely during combat, his environment had to be prepared before the fighting began. He reached beneath the seat and plugged in his electrically heated suit, connected his oxygen hose into the regulator, checked that the oxygen gauge read around 400 pounds per square inches, verified that the oxygen flow indicator was active. The ball turret used a completely independent oxygen system. It had to. If it relied on the bomber's main oxygen line, the rotating turret would twist the hoses until they tore apart, a fatal failure at high altitude. Instead, a dedicated oxygen bottle rotated with the turret, giving the gunner about 2 hours of breathable air before the waste gunner had to replace it. Microphone, communications, and combat switches. Inside the turret, the gunner had no free hands. Both were required to control firing and movement, so communication had to rely on instinct. A small push-to-talk switch was located near his right heel, operated by tapping with his foot. On the switch box were the gun selector switches, one for each. 50 caliber machine gun. These stayed off until combat. Why? Because the firing buttons sat dangerously close beneath the gunner's thick mittens. One accidental brush could fire bullets into the bomber itself. Charging the guns. This was one of the strangest rituals in the entire B-17. Normally, a Browning 50 caliber machine gun was charged by pulling a heavy handle, but inside the ball turret, the charging handles were near the gunner's ears, completely impossible to pull in his cramped, folded position. So engineers designed a pulley-based charging system. Two cables ran from each gun's slide assembly, routed through pulleys, ending in two handles near the gunner's feet. The gunner leaned forward, crossed his arms, gripped the handles, and pulled them toward his chest, sliding the bolts back to charge both guns. The Sperry ball turret didn't just hang under the B-17, it rotated, elevated, powered itself, and stayed electrically connected while spinning in every direction. For a system built in the early 1940 seconds, the engineering was astonishing. A floating sphere under the aircraft. The heart of the system was the 46.5-inch opening cut into the belly of the B-17. Into this opening sat a slightly larger trunnion ring, a circular support frame that held the entire turret in place. Attached to the top of the turret was the trunnion ring support assembly. It carried the weight of the turret, rotated freely as the gunner moved the sphere, acted as the anchor point connecting the turret to the bomber's fuselage. This ring was incredibly strong. It had to handle the recoil of two 50 caliber machine guns, rapid rotation, and the violent maneuvering of a bomber under fire. The harness, the turret's skeleton and electrical lifeline, bolted onto the support assembly was a structure called the harness. It served two jobs. 1. Structural reinforcement. The harness braced the turret to the airframe, preventing wobble or mechanical stress as the sphere spun. 2. Electrical power conduit. This was the genius part. All power to the turret flowed through the harness using a special set of rotating brush connectors. The turret could spin endlessly in either direction. Wires never twisted, stretched, or snapped. Every electrical system stayed powered, no matter how fast the gunner moved. For 1,940 seconds engineering, this was cutting edge. A perfect marriage of mechanics and electrics. The swivel bracket. At the top of the harness sat a free-spinning swivel bracket that allowed the entire assembly to rotate smoothly. Without it, the turret would grind, bind, or tear itself apart during rapid turns. Full rotation movement. When powered, the Sperry ball turret could rotate 360 degrees in just 8 seconds, elevate or depress 90 degrees in 3 seconds, move vertically and horizontally at the same time. Respond faster the harder the gunner pushed the control grips. This meant the gunner could track fighters racing underneath or around the bomber at blistering speeds. The propeller safety cam. Located on the turret ring was a forward-facing safety cam, a shaped metal ramp. When the turret pointed forward, a pin connected to the turret touched the cam. This cut electrical power to the firing solenoids. Why? So the gunner could never even by mistake fire the 50 calibers into the B-17's own propellers. A simple but brilliant mechanical failsafe. Unfortunately, the cam did not account for open bomb bay doors, meaning the gunner could accidentally shoot the doors during a bombing run. The Sperry ball turret was one of the most complex defensive systems of World War II, a machine so advanced that only 3 factories in the entire United States possessed the equipment to build it. Each unit cost the equivalent of $250,000 today, and astonishingly, a quarter of that cost came from a single component, the Sperry K4 automatic computing gun sight, a shoebox-sized mechanical computer that allowed a cramped gunner to predict enemy movement with remarkable accuracy. For its time, the ball turret was a marvel, compact, deadly, and mechanically elegant. But like all wartime technologies, its era eventually ended. As jet fighters, electronic warfare systems, and guided missiles arrived on the battlefield, the idea of a manned, rotating gun turret became obsolete. Remote weapons, radar-guided defense, and automated systems took over roles once assigned to brave young gunners curled up inside a steel sphere beneath a bomber. Yet the legacy of the ball turret remains powerful. It is remembered not only for its engineering, but for the courage of those who operated it, servicemen who endured freezing temperatures, crushing confinement, and constant danger to protect their crew from attacks below. Today, the turret stands as one of the most iconic symbols of the B-17 flying fortress, and of a generation whose ingenuity and resilience shaped aviation history. If you enjoy breaking down complex machines like the Sperry ball turret, or want to strengthen your technical thinking, we highly recommend exploring Brilliant. Brilliant specializes in first principles learning, helping you understand concepts from the ground up through interactive problem solving. It's been shown to be 6 times more effective than passive lecture videos. Their courses cover mathematics, data analysis, computer science, physics and engineering, advanced problem-solving skills. All lessons are built by an award-winning team from MIT, Caltech, Duke, Microsoft, Google, and more. And they're designed for real mastery, not memorization. At IM Blueprint, we frequently use Brilliant to understand the engineering foundations behind historical weapons systems, aircraft mechanisms, and complex wartime technologies. It helps us produce accurate, deeply researched videos like this one. You can try everything Brilliant offers free for 30 days using the link in the description. After that, you'll also get 20% off an annual premium subscription. If you spot anything we missed in this video or have questions of your own, feel free to leave a comment. We're always improving. Thank you for watching.